So are you talking, sir?
Can you hear me?
Yes,
Yes,
now
sir. Now
can.
can clear.
So earlier you couldn't hear anything, is it?
Yep. Yep.
Okay, so I don't know what's the issue. So, so in between, so I will start my lecture now. So in between, if you any silence, so please prompt me so that I can be alert. Okay, I will start again. Okay, so today we will cover pressure measurement devices. Okay, section 2.8. So normally a pressure we will measure with certain devices. Nowadays in the hospitals, so we can have the digitalized system to measure the pressure. But those time we often use a barometer. So barometer is a pressure measurement device. So in the barometer, atmospheric pressure is measured by a device, by the device, and because of that, atmospheric pressure will be always called referred to as a barometric pressure. So barometric pressure is from the barometer. So baro is always referred to pressure. Okay, so you know that when I say barometric pressure in the exam, so you know it is referring to the atmospheric pressure. So this is the basic setup of barometer. Okay, so you'll have in this case a mercury. So we always use a different fluid. Okay, so we know mercury is having a different density than the normal air and also the water. Okay, so we will measure 2 points. So we know here we have a vacuum. Okay, because nothing here. So at C, the pressure will be zero, and because of the gravity, so we will have a weight in the molecules, and here at point B, it will be atmospheric pressure because it's exposed to the surrounding. Okay, so the atmospheric pressure, so at P8 atm, so atmospheric pressure equals to rho gh. Okay, for this case. Okay, frequently used pressure unit is the standard atmosphere, which is defined as the pressure produced in the column of mercury 760 mm in height. So the height is 760, and at 0 degrees, so mercury's density is 13 times of water, so 13,595 kilogram per meter cube under standard gravitational acceleration, 9.81 usually. Okay, so the length or the cross sectional area of the tube has no effect on the height of the fluid. Okay, so the height usually will be the same. Okay, so unless it has some capillary effect. Capillary effect is something that holds the meniscus. Okay, so that it will differ according to the cross sectional area or the length of the tube. So if you can do the experiment in the house, so maybe you can take a basin of water, and you just put the cup in an inverted position into the water. So you will see the water level will rise inside the cup, and usually at the different parts, so it will be at the same level. Okay, so unless you have a capillary effect. Okay, so this is a manometer. So manometer is commonly used to measure small and moderate pressure differences. Okay, manometer contain one or more fluids such as mercury, water, alcohol, or oil. Okay, so this is a simple manometer. So manometer can be used in various applications. So it can be used in medical. So it can be used in an aircraft. Because even in the aircraft, we need to know the surrounding pressures that it can withstand. it is facing. So manometers can be any point of the application where the pressure is measured. Okay, so this is basic setup. So usually it will have one or more fluid. Okay, so you can have one or more fluid. Here we have one is the gas and one more is another liquid. Okay, so you can have a few liquids joined together in order to measure. Okay, so here how the measurement is taken. So we know, so pressure will be the same at the same height. Okay, so it will be the same at the same height. So just if it's having a different material or different type of liquid, so you need to consider the density as well. Okay, so this case, so we assume that the pressure at 1 and 2 at the same height will be the same. Okay, so it can give a equation for us to start with. Okay, so pressure at 2, P2 equals to, so the atmospheric pressure plus rho gh. So this one we know. Okay, so pressure at 2 will be atmospheric pressure plus rho gh. Okay, and when we have a multiple liquid, so we need to consider the different densities. So in this case, so we have a container and atmospheric pressure at the top. So pressure at point 1 equals to atmospheric pressure plus rho gh1. So I1. So because this is a fluid one, different density, rho 1 gh1. Then we have rho 2. Okay, different density, rho 2 g, gravity will be the same, and h2 plus rho g, uh, rho 3, uh, okay, rho 3 g h3. Okay, so all these things, if you mix, so you can find the pressure at point 1. Okay, so this is the basic principle that we will use in the manometer calculation. Okay, and we have uh, another setup of manometer where it can be used to measure pressure drop across a flow section. So we have a flow section here, dotted area or flow device by a differential manometer. So differential manometer, it will find differences of pressure between point 1 and point 2. Okay, so here yeah, we have 1 and 2, and here you can see, so the manometer. Okay, the manometer. So here it will be water. Okay, so we assume it's a water. Okay, because it's blue in color. Okay, so the water will have its own density. So density 1, and the orange uh, liquid is another fluid. So we consider it as a density 2. Okay, so here you have A1. So that's the height from this line to this line, and H is from this line to this line. Okay, so we start with the first first assumption, so where the pressure at these 2 points A and B is the same. Okay, so put aside the density different, but we know that from this I to here, so it will be the same. Okay, so A and B should be the same. Okay, so pressure PA equals to PB. Okay, now we bring in the density. Okay, density, so where the differences will be there. Okay, so first we calculate for PA. So what is PA? So we know from here to here, there will be the pressure A. Okay, PA. So PA is, so P1. So P1 from here, pressure point 1. So 1, and you take into consideration rho G. Okay, so row one gravity plus, so the height from point 1 to point A is A plus H. Okay, so H plus A. Okay, so we know the equation for pressure A. Okay, so is this. Okay, so equals to, so now we find PB. So PB a bit tricky because it's having two materials. So we need to consider from point 2 until point B. Okay, so we start with P2. So pressure 2 plus, uh, first we calculate for the water. Okay, so row 1, because we know row 1 is the same. So row 1, gravity the same, height is A. Okay, plus row 2, so that is the density for the second material. Okay, gravity and H. Okay, so we already know both equation. Okay, so this for uh, PA and this is for PB. Okay, now we rearrange the formula. Okay, so we rearrange the formula. So pressure, we can bring it to this side because we want to measure the pressure drop. Okay, pressure drop. So P1 minus P2. Okay, then you rearrange all this. At the end, you will get this formula. Okay, so row 2 GH minus row 1 GH. Okay, so you simplify it, you'll get P1 minus P2 equals to row 2 minus row 1 GH. Okay, so this is the formula that you can apply. Okay, so you no need to do a lot of calculations, so you just need to substitute the value. Substitute the value inside here, and you will get the pressure difference. Okay, so other pressure measurement devices available. So we have a Borden tube. It consists of a hollow metal tube and like a hook whose end is closed and connected to a dial indicator. So we usually will see this, but inside the mechanism will be like this. So the pressure will enter. So we have a hollow tube, a metal tube inside. The meaning nothing inside. So it's a hollow. So kosong lah. So in bahasa Melayu is called kosong. So when the pressure enter, so the pressure will go through the hollow tube. So when the pressure is entering, so it will become straight. The tube will become straight, and the dial will start to move. So it will start to move from zero to whatever pressure. Uh, so once the pressure is released, so the hollow tube will become like circle back, and it will go back to zero. Okay, the dial will go back to zero. So that is a Borden tube. So usually we will see this in a production line. So even in the house, we can see at at the outside. So if you have a water filter, okay, attached to your piping system, so you will see a pressure gauge on top. So that is actually a Borden tube. Okay, then we have a pressure transducers. Okay, modern world, so we have more electrical based pressure sensors. Okay, so you use various technique to convert the pressure effect to an electrical effect. Okay, normally the sensors, what it will do, it will receive from the environment or from the human or the mechanical system. It will convert it into an electrical effect. So it will have a change of voltage, change of resistance or capacitance. So normally these three. So based on that, we will get a digital value which we can use in our microcontrollers or in our computation in the computer. So we have a pressure transducers. So pressure transducers are smaller and faster. Okay, and they can be more sensitive, reliable, and precise than their mechanical counterparts. So mechanical counterpart is the Borden tube. So it's more accurate. So more accurate, more faster, because nowadays we want a faster response. So we want things to move in a fast rate. So we can consider using pressure transducers in our system. Then we have a strain gauge pressure transducers. Okay, work by having a diaphragm effect between two chambers open to the pressure input. So normally, strain gauge, it will be elastic. The elastical pressure transducer. So it's a type of pressure transducers, but it depends on the extension or retraction of the material. Uh, so based on that, so you will have a diaphragm inside. So and the diaphragm will expand or uh, it will retract. So based on that, the electrical signals will be generated. Then we have piezoelectric transducers. So we have a solid state material, crystalline material inside. Then it is also called solid state pressure transducers. So all these are pressure transducers. Okay, so it will work on the principle that electrical potential is generated in a crystalline substance when the subject to mechanical pressure. So if you give a mechanical pressure to the piezoelectric transducers, so it will generate a electrical. So more or less all these are the same because all are pressure transducers, but the differences will be on the mechanism how you give the pressure and to what it will convert, whether it's to voltage, resistance, or capacitance. Okay, so we have completed chapter number 2. Okay, so we have covered the systems and control volumes. So we have covered the properties of the system, then density and specific gravity, states, and also equilibrium position. Okay, then we have processes and cycles we have learned. So temperature and also zeroth law of thermodynamics we have covered yesterday. Okay, then we have seen on the pressures, and today we have concluded the chapter with the pressure measurement device. Okay, so all these are some of the introduction to the thermodynamics. Okay, so we have learned a lot of principles, a lot of terms used in thermodynamics. Okay, all these terms will be used throughout this course. Okay, throughout the 9 chapters that we are having, so we will continuously use. So if you don't know any of the terms, so you refer back to chapter number 2. Okay, some we already discussed. Okay, so any questions so far before we go to examples? So I have a few examples, few questions that we can try. Okay, so this is not tutorial, but it is just like a questions for you to understand better. So any questions so far from the slide today? No question. Can you still hear me?
Yes, doctor.
Okay. So hope you already understood whatever we have studied. So I will open uh, the slide for example. Okay, so this slide I haven't upload in the system in the Google Classroom. So I will upload today together with all the videos for this week and also the Ed Puzzle assignment. So those who didn't attend, any of your friends didn't attend, or you didn't attend yesterday's class, so you can always go to Ed Puzzle, settle the videos, and get your attendance. Okay, so no reason for you to say I couldn't attend or exemption because the videos are always there and you are given ample of time to listen. You have like 1 week, okay, 4 to 5 days before the next class. for you to listen and score your attendance. Okay, so we will go to the examples today. Okay, so we will see around 6 questions, simple questions, very direct questions. Answer are given, so you can just revise and understand the concepts better. Okay, so this is your example number one. Okay, so example number one is related to temperature conversions, temperature point conversion. So yesterday we have studied on this. So we know there are. Can you hear me? Is there
Yes,
any?
doctor.
Yes, yes, doctor.
Okay, so I think someone is unmuted. Okay, so it's okay. Okay, so yesterday we have seen the temperature scales. So we have Kelvin, so we have Celsius, then we have Rankine, and also the Fahrenheit. Okay, so I have told you that there will be some questions at times, directly or indirectly, will ask you to convert to different scales. Okay, so here we can see this example number one. During a heating process, the temperature of a system rises by 10 degrees Celsius. So the question gave you the answer, the first information in the Celsius. So you are required to express the rise in temperature in Kelvin, Fahrenheit, and also Rankine. So the key word here is it says that temperature rises by 10. So meaning that is a temperature difference. That is not the actual temperature. So it is actually the delta. So delta means the changes or changes in the temperature. Okay, so the changes in temperature in Celsius is 10 degrees Celsius. So we know yesterday I already given. So maybe you can refer back to chapter number 2, yesterday's slide. So all these formulas are given there. Okay, so changes in temperature for Kelvin is actually changes of temperature in Celsius. So we already know the changes of temperature in Celsius in 10 degrees Celsius. So the changes in temperature in Kelvin is 10 K. Okay, so 10 Kelvin. Okay, so that's the first part. So we have answered for Kelvin. Then the second one, so we know from these two information that we have obtained. So see which one you can solve first. So because the third one, even though the question says us to find f first, so f, for you to find f, you need to know the value of r first. So you need to find r first. Okay, so the changes of temperature in Rankine equals to 1.8 times changes of temperature in Kelvin. So this one we already know 10 Kelvin. So 1.8 times 10. So we the answer is 18 Rankine. Okay, so once you already find this, so we already can use this formula to find the changes of temperature in Fahrenheit. So changes of temperature in Fahrenheit equals to changes of temperature in Rankine. So the final value is 18 degree Fahrenheit. So make sure you use the proper units to differentiate. So Fahrenheit and Celsius. So normally we'll have the small degree, and Rankine and Kelvin. You won't have that. Okay, so don't put degree Kelvin or degree Rankine. So it's a wrong reading. So the mark will be minus because you are giving a wrong units. Okay, so any question for example number one? I think it's a bit direct. So I hope you can understand. Okay, so then we move to example number two. Okay, a vacuum gauge connected to a chamber reads 40 degree, 40 kilopascal at a location where the atmospheric pressure is 100 kilopascal. So determine the absolute pressure in the chamber. So absolute pressure is the actual pressure. Okay, so actual pressure that we can measure. So yesterday I already explained this. Okay, so it start with atmospheric pressure. Okay, atmospheric pressure will change according to the height, height of the surface. Okay, so if you are at the sea level, so the atmospheric pressure will be uh, normal, and if below sea level, the atmospheric pressure will be higher, and if on the hill, so the atmospheric pressure will be lower. So it's all because of the gravity and the distance from the earth core. Okay, so we know this atmospheric pressure. So if the pressure is higher, the one that you are measuring is higher, so we call it as a gauge pressure. And if the pressure that you are measuring is lower than atmospheric pressure, we call it as a vacuum pressure. Okay, then we have the absolute zero pressure, where in the perfect vacuum condition. So in the earth, we know that you cannot recreate a perfect vacuum condition. In the lab, you can produce almost vacuum. Okay, so there still will be some gravitational effect, and because of that, you'll have a certain value of pressure. So from zero, if you calculate until gauge pressure, that is called the absolute pressure. And from zero pressure until the vacuum pressure, so whatever pressures that you are measuring, either vacuum pressure or gauge pressure, from the zero value, we call it as a absolute pressure. So this case, so we are getting some key points from the question itself. So it is saying a vacuum gauge, even though it says a gauge, so it is a vacuum gauge. So meaning we know it is measuring a vacuum pressure. So we know that you need to minus the absolute value. So absolute value, you need to minus atmospheric pressure with the vacuum pressure. Okay, so the question already gave you few keywords. So vacuum gauge, so we know it's a vacuum pressure, and the vacuum gauge measure 40 kilopascal. So atmospheric pressure we know is 100 kilopascal. So you need to find the absolute pressure in the chamber. So absolute pressure equals to atmospheric pressure minus vacuum pressure, because atmospheric pressure is higher, so you minus with the lower. Okay, so if the question is saying the gauge pressure, so you need to plus. So atmospheric pressure plus gauge pressure. So if it's higher, but since you're finding a vacuum, so you need to minus. Okay, so atmospheric pressure is 100, and the vacuum pressure is 40. So you need to minus 40. So the absolute pressure from year to year is 60 kilopascal. Okay, so I hope you can understand the concept. So you can try, you can get the book or the question from the internet, and you can try yourself. Okay, for different questions, and we also will try to cover this kind of questions in the tutorial. Okay, so we move to example number 3. Okay, determine the atmospheric pressure at the location where the barometric reading. So barometric reading is a keyword. So it's referring to. Uh, okay, so it's okay. We read first. So barometric reading. So barometric reading means from this point to this point, how much the water is rising. Uh, so barometric reading is not referring to the atmospheric pressure unless it says barometric pressure. Then it is referring to atmospheric pressure. Barometric reading means is the reading of the barometer, which is the height. Okay, so H is given 740. So the reading in the barometer will be millimeter mercury. Okay, so this one you can convert to millimeter. Okay, millimeter, because it's a height. Okay, and the gravitational acceleration is given. So if in the question they gave a specific value, is more accurate gravitational value. So 9.805. So if it's given like this, you need to use this value. If it's not given in the question, you can assume it 9.81. Okay. So in this case, you need to use. So assume the temperature of the mercury to be 10 degrees Celsius, at which its density is 13,570 kilogram per meter cube. Okay, so all the values are given. Okay, so you need to know. Okay, so this formula is given in the lecture note earlier. So atmospheric pressure, because you want to measure the atmospheric pressure here, so it is rho gh. So rho gh, because you are starting from here. So since point B equals to atmospheric pressure, so we are actually calculating the pressure at point B. So rho gh. So rho gh is rho, we know, is 13,570. Then gravity is given 9.805, and H is a bit tricky because you only give the barometric reading, but we know from here, so 740 millimeter mercury is actually referring to the height from this point to this point. So it is actually 740 millimeter, but in the question you cannot use 740 millimeter, so you need to convert it into meters because SI unit. So 740 millimeters is equivalent to 0.740 meter. Okay, so this is your unit conversion. So we use unit conversion based on the formula. So if you see this, 1 Newton divided by 1 kilogram per meter per second square is actually equals to 1. And 1 kilopascal divided by 1000 Newton per meter square is equals to 1. So if anything times with 1, it still carries the same value. So that's why we use this unit conversion based on the units available here, so that you can cancel it immediately from the equation. If not, you need to find this first, then you need to have a converter to convert it to kilopascal, especially if the question mentioned you need to give the answer in kilopascal. So normally in thermodynamics we will use this unit conversions. Okay, so get some practice how to use this unit conversion. So here you can cancel like kilogram, you can cancel with kilogram. So meter cube, you can cancel with meter. So you have a meter here and you have meter square here, so you can cancel. So after you cancel everything, only left kilopascal. So you can directly take the value, so 98.5 kilopascal. So the pressure at point B is 98.5 kilopascal. Okay, so you can understand. Okay, the pressure at point C is 0 because you have a vacuum here. So that's why the pressure here is 0, and here the pressure ATM. So which is pressure P. Okay, can you understand? So far, can follow? Can? Okay. So if you have questions, you can ask. Okay, so we go to a few more examples. Okay, example number 4. So intravenous infusions usually are driven by gravity by hanging the fluid bottle at sufficient height to counter-react the blood pressure in the vein and to force the fluid into the body. Okay, so this is how the intravenous, okay, so like this in the photo. So normally how the pressure from the bottle and on the liquid or the blood, so whatever things it can enter to human body, because our human body we already have nerves, so which already have a pressure. So if the pressure is not high, so the liquid will not enter into our body. So we have a specific setup and specific height for you to hang the fluid bottle for it to counter react to the blood pressure and force the fluid into the body. Okay, so that's the principle behind it. Okay, so the higher the bottle is raised, the higher the flow rate of the fluid will be. Okay, so when you fix the bottle, so it must be at the certain height. It cannot be too high or too low, because it will have a different effect. Okay, so if it is observed that the fluid and the blood pressures balance each other when the bottle is at 1.2 meter above the arm level. So meaning, so at 1.2 meters, so the fluid pressure and the blood pressure are the same. Okay, are the same. So it's some information here at the arm level. So arm level is here. So determine the gauge pressure of the blood, and B. So if the gauge pressure of the fluid at the arm level needs to be 20 kilopascal, so meaning the pressure here 20 kilopascal, determine how high the bottle must be placed. Okay, so take the density of the fluid to be 1020 kilogram per meter cube. So that's why, just some information. So in the hospital, so let's say they are injecting some fluid inside your body. So that's the reason why they always will measure your blood pressure, because they need to adjust the height of the bottle based on uh, your blood pressure. So if the blood pressure is too high, so you need to place the bottle too high. So they will wait. They will give the blood pressure reducer or the pills for the blood pressure to reduce first. Then they will give the fluid inside your body. So that's the reason why during the operation they will check the blood pressure also. Because if the blood pressure is too high, they need to wait until the blood pressure is reduced. If not, if they cut you open or they want to do operation, so the blood pressure, the blood will splash everywhere. So these are the things that you can understand additionally. Okay, so when you understand that concept, you know how to design your system. So we as an engineer, we will design the system based on the requirement, and we need to do all this analysis. Okay, so all this information are given. So there are two parts of the question. So it says that if it is observed that the fluid and the blood pressure balance each other when the bottle is 1.2 meter above the arm level, so they are asking us to find the gauge pressure. Okay, so the answer is given here. Gauge pressure at the arm equals to, so absolute pressure minus atmospheric pressure. Okay, so atmospheric pressure is here and the absolute pressure is here, and we are measuring at this point. Okay, so at this point. So we need to minus the atmospheric pressure. So absolute pressure minus the atmospheric pressure. So we know that it is a rho gh, even though is opposite. So arm to bottle. So not, so usually we will measure uh, from top to down. So this one we are measuring down to up. So when it is opposite direction, so it's going up. So we need to minus. So we need to minus. So we will see in the other example about this. Okay, so uh, here, so absolute pressure minus atmospheric pressure. So the equation is rho gh, arm to bottle. Okay, so here we know rho is given, density of the fluid is 1020. So kilogram per meter cube. So gravity is not given, so you can take 9.81. Okay, so 9.81 meter per second square, and the height is 1.2. From the end to the bottle is 1.2 meters, and this is the unit conversion. So after you solve this, you will get the gauge pressure is 12 kilopascal. Okay, then we enter to the second question. So if the gauge pressure of the fluid at the arm level need to be 20 kilopascal for sufficient flow rate, so determine how high the bottle must be placed. So take the density. This is the same lah. Okay, so you want to find, because earlier you found that at at 1.2 meters, the gauge pressure is 12 kilopascal. So it's not sufficient. It will cancel out the blood pressure. So meaning the fluid will not enter the body. Okay, so they say you need to have at least 20 kilopascal here in order to fluid from the bottle to enter the body. Okay, so you need to check. So each arm to bottle, okay, equals to gauge pressure at arm divided by rho g. So this is actually from this equation. So pressure gauge equals to rho g h. Okay, so rho g h. So here you rearrange because you want to find the height, and new gauge pressure already given. So they say here 20 kilopascal. So 20 kilopascal divided by rho is 1020 and G is 9.81. Unit conversion you are having here. So after you check, you solve it. So you know that the height that requires is 2 meters. So when the height of the bottle from the body is 2 meters, so the pressure will be sufficient for the fluid to enter the body. Okay, so that is number 4. So try to understand how we are solving this question. So then we will enter example number 5. Okay, a manometer is used to measure the pressure of a gas in a tank. The fluid use a specific gravity of 0.85. So specific gravity we studied in part 1. Okay, so last week. Okay, and the manometer column height is 55 cm. Okay, so here is 55 cm as shown in figure 2.39. Okay, so if the local atmospheric pressure, so local atmospheric pressure is surrounding is 96 kilopascal, so it's given here. So determine the absolute pressure within the tank. Okay, so here you have a, I believe it's a gas because it's a gas tank. So here you have a pressure, and here you have a liquid with a specific gravity of 0.85. Okay, so specific gravity will always relate to the gravity, the density of the water. Okay, so density of the water. Okay, so here first you need to calculate so the density of the fluid, because only specific gravity is given. So for you to substitute here, you need to know the density. Okay, so the formula is specific gravity times with density of water. Okay, so specific gravity is given 0.85 times with 1000 is the density of water. So the density of this fluid is 850 kilogram per meter cube. So you already found this, then you can replace it here. Okay, so we want to find the pressure. So pressure of this gas. So pressure of this gas is actually the same pressure at this point. It's similar like how at this surface, uh, the pressure is atmospheric pressure because it's connected. So similarly, so this is connected to this point at this fluid at this point. So we will measure the pressure at this point because it will be the same. So pressure here is actually atmospheric pressure plus rho gh because it's going down. Okay, so it's going deep. So you need to plus. So atmospheric pressure plus rho gh. I believe all the information are already obtained. Okay, so atmospheric pressure is 96. Rho is 850. You measure here. So 9.81. Gravity is not given, so we can take 9.81. And the height is in cm, you convert to meter, 0.55 meter. And these are the unit conversions. Okay, unit conversions so normally will have one or you will have two or more. So depends on the units available here. Okay, so after you solve all this, so the pressure at this point is 100.6 kilopascal. Okay, so that is the example number 5. So all these are quite common questions, so quite easy because it is only single fluid. Okay, so you suppose if you understand the concept, you can do. Okay, so we are entering to the last question for today. Okay, so the water in a tank is pressurized by air. Okay, so you have air here and you have a water. So we know that at point number 1, point A, so the pressure of air and pressure of water will be the same. Okay, similar like at point 2, point D. Okay, so atmospheric pressure and pressure at 2 will be the same. So that is the concept that we already know. Okay, so the water in a tank is pressurized by air and the pressure is measured by a multi-fluid manometer as shown in figure 2.42. So if you see you have water, then you have oil and you have a mercury. So that is what we call as a multi-fluid. So when three different liquids are used, so we know it will carry different densities. Okay, so a tank is located on a mountain at the altitude of 1400 meters where the atmospheric pressure is 85.6. So normally the altitude value is not so crucial. uh, the main thing is we know that atmospheric pressure at the higher height will be lower, so that's why the value is 85.6. So for your application, so you just need to take the value and just use because it's given. So the question is asking determine the air pressure in the tank. So if H1 is 0.1, so H2 is 0.2 and H3 is 0.35. So take the densities of water, oil and mercury to be 1850 and 13,600, so respectively. So densities are given, height are given, and also the atmospheric pressure is given. So how to calculate the multi-fluid? So if you see we are starting here. We are starting here. Okay, so we want to calculate um, starting from this point. Okay, so this point. Okay, so we know that if the height is going down, so meaning first we want to calculate from here to here, then we want to calculate from here to here, then third we want to calculate from here to here. So A to B, so B to C, then C to D. Okay, so we know that when you go down, when you go deeper, you need to plus. So that's why you have plus here. And when from C to D is going up, so going up, you need to minus. Okay, so you need to minus. So we need to know this. So A to B to C, you need to plus, then C to D, you need to minus. So that's why you get the equation. Here you get plus. Okay, so we will start analyzing one by one. Okay, so we know all this will be equals to point pressure number 2, and pressure number 2 is actually the atmospheric pressure because it's sharing the same contact point. Okay, so we know um, okay, we calculate for P1 first. Okay, so P1, so P1 is the one that we want to measure. Okay, then we have water here. So water here, so is we want to measure the point here. So it's actually similar like the water density. So water density we already know. So G H1. So H1 is from this level to this level. So H1 we already know. So it's a plus because it's going down. So then we want to find from point B to point C. So we have a different material from year to year is the oil. Okay, so the density of oil times with gravity times with H2. Okay, then from point to this point, we have a density of mercury. So gravity times H3. Okay, so we already know all this. So all these are equals to P2. So pressure at 2 and pressure at 2 equals to atmospheric pressure. So you already got this. So you try to rearrange. So rearrange, you will get the formula like this. Then you substitute the value. So atmospheric pressure is 85.6 kilopascal. So gravity is 9.81. So here you already simplify it. So density of mercury is 13,600, and H3 is 0.35, uh, and minus 1000. So it's the density of water. So times with I1, so 0.1. So minus, so density of oil 850 times with 0.2. Okay, so you already know, then unit conversions. So once you solve all this, so you'll know that pressure 1 equals to 130 kilopascal. Okay, so this is how you solve multi-fluid manometer questions. Okay, so any questions so far? Okay, so we have seen 6 examples. I will upload all these examples in the Google Classroom for you to study by your own. So if you have questions, you can always ask me. Okay, so any questions so far? If no questions, I will take attendance. Okay, please hold on. Okay, as usual, I will open the link for 5 minutes. So I will share the link in the chat box. Okay, so I already shared. So once you fill up the attendance, so you can leave the chat. So thank you. We will meet next week.
Thank you, Doctor.
Thank you, Doctor.